Okay, so occasionally we will work with bases other than E. That'll show up every now and again. So we'll call it base A. That could be any value that is not equal to 1, right? Because if A is 1, that's not a very interesting function. And it's got to be positive, okay? So, and this is the same A as we defined it when we studied exponential functions a long time ago. So you might remember this relationship, e to the natural log of a, right? You remember those guys canceled each other out. They're the same base. So if I just raise both of those to x, I can define my exponential function a to the x as base e, right? These are the same thing. So e to the ln a times x, right? We can multiply those guys, is equal to a to the x. And that's all we need to do the calculus on a to the x, to think of it like this, and we can get all of our results, because you know how to take the derivative of e to some function of x. And you know how to integrate that as well. Okay, so let's do it. So if a to the x is e to the ln a times x, then the derivative of a to the x, which is what we're trying to find here, right, is equal to the derivative of e to the natural log of a times x. And we already did these, right? The derivative of e to some function of x is e to that function of x times the chain rule times the derivative of the exponent. Okay, so the derivative of a to the x, which is the same as the derivative of e to the ln a times x, is equal to e to the ln a times x times the natural log of a constant. Right? And now we can go back and substitute that with a, or the whole thing as a to the x. And typically you'll see this written out front. So the derivative of a to the x then, just like e to the x is its own derivative, but we have an extra factor, ln a. And if I want to integrate this guy, the antiderivative of a to the x would be, you might guess, it's going to have its own function in there, right? But think about it. If you want to take the derivative of a to the x, right, if you want to go backwards and you need to get just a to the x, then you're going to need a constant here, right? So if you take the derivative of this, you get a to the x times ln a. So that would show up. So you would need to cancel that guy out. And now do your check. Take the derivative of that. Derivative of a to the x is ln a times a to the x. This would come along for the ride and they'd cancel out and you'd be left with that. So there you have it. Those are your two formulas for a to the x. It just involves a extra, you just got to remember where to put it, an extra constant that is the natural log of the base. And so now we can talk about the log function. Okay, so if you remember your change of base formula, the log base a of x, if I want to change this to base, the natural base, then it's going to be the natural log of x over the natural log of a. It's from your change of base formula. And then we can write it like this if we want to pull out that constant, right? Because ln a, of course, is just a constant. The x is our function, or ln x. Okay, so what do we want to do next? Take the derivative of this guy. All right, let's do it. You know how to do that. The derivative of the log base a of x, right? That's our goal, to be able to deal with other bases, would be equal to the derivative of 1 over the natural log of a times the natural log of x. And we know how to do this. The derivative of the ln x is 1 over x. The derivative of, well, the constant times this, constant multiple rule, so that's just going to come along for the ride. All right, and there's your derivative of the log base a of x. It's the same as the natural log derivative, only you get a multiple of 1 over ln a. Okay, that's it. Pretty easy. Now with integration, you probably aren't really going to see this, because think about it. What we did with the exponential, we go backwards, right? So am I going to ask you to integrate something like this? Probably not, right? That is, you'd have to start with something that looks like this and go backwards. So you won't really have to worry about integration with this. We still know that this is the natural log. And if it so happens that there's somehow 1 over ln a, this could be the log base a. All right, but most likely you won't see that. So you're not going to see a formula. You're not going to see that formula. Okay, you don't have to worry about that for integration. So basically, what do we have? We have three new formulas. The derivative of a to the x equals the natural log a times a to the x. The antiderivative of a to the x is itself, but times 1 over the natural log of a plus c. And then we have a derivative for log base a. That's any a, how we defined a, right? Positive number not equal to 1 is going to be that guy. All right, and then of course, whenever we have the function for x, here's the ones I just highlighted. I highlighted that guy, and well, that was it, and then we have the integral. But of course, anytime we get a formula for a function of x, we get the chain rule equivalent, right? This can be a u, and you could have to do the chain rule thing. All right, so let's try a couple. These are pretty straightforward, I think. Y prime equals, when I see an exponential, I just rewrite it. And then what do I need? I need a natural log of 2 to multiply by that. That's it. Okay, this requires the chain rule, so think about this. When I take the derivative, this is going to show up. I'm going to need a natural log of 2, but don't forget the chain rule, du dx. This is my u. So du dx would be 3. Derivative of 3x is 3. And most of the time you would see the constant written. Remember, that's a constant, ln2 constant, not a function. Most of the time you see it written like that. Okay, let's do this for log base a, where your base is 10. So y prime is equal to, think of the natural log, because we're familiar with this one, right? It's going to be, this is a composite function, so it's going to be u prime over u, right? This is the chain rule version. So u prime over u. And then we divide by there's an extra step, just one extra step. So if we pretend like this is a natural log of cosine u, you would say u prime over u, right? If that were ln, and then we'd be done. However, it's log base 10, which means we need an extra factor of the natural log of 10. And then if we want, we can recognize that as the tangent function. So negative 1 over ln 10 tangent x. Okay? Not too bad. If you can do log, the natural log, which would be that, then you can just tack on the extra constant needed. And same goes for exponentials. And then here is our formula for the antiderivative of an exponential. So those are pretty straightforward too. Just try not to get these confused with the derivative of the log of base a, because they both involve dividing by natural log of that base. So this is easy, equals. So I see an exponential function. I know it's going to show up in its own antiderivative, just like it would for its derivative. I know I need a plus c. And then anytime that's base is not e, you're going to need an ln of that base. You just have to decide where to put it. And when you're anti-differentiating or integrating, it goes in the denominator. Okay, so that's it. That's a real brief video on base other than a. From your textbook, that goes with 5.5.